In this video, I wanted to walk through the brew-debug-host and talk about how it implements the debug adapter protocol and then converts that into operations where it calls into our code. So if you remember in our main method, we're creating a debug server. So this is the entry point for everything. And the start method is given an execution engine, right? So in this brew-debug-host, here are all the definitions of the interfaces that the code in our VM needs to implement, right? We had to extend the execution engine class. We needed to implement iFunction, iStackFrame, iThread. So this is basically how our code is interacting with this host. So back here in the server, when it started, it's going to create a server socket on the port 8888. Looks like that's not configurable at the moment. I thought I had made that configurable. So this is going to listen on a port. That's a standard Java class. And then we're just going to accept a connection. Whenever we get a connection, we'll create a protocol server to handle it. We give it the input and output string for that connection. And we give it a factory that will create a debug adapter. And then we call run on that protocol server. So the protocol server is going to use this debug adapter to do all the work. The protocol server will listen to the network connection and interpret the commands that come in. And then when we return responses, it will turn those back into JSON and send them over the wire. So the protocol server basically receives messages on the wire, turns them into objects, takes our objects, turns them back into network messages, sends them back to VS Code. So this debug adapter is sort of the heart of this whole thing. We have our protocol server. We have a host thread. This host thread is a class that will actually be controlling the execution of our VM program. We have a Boolean to tell if we have launched the debug session yet or not. And we have a string for the root of our workspace. This is the path to the folder our workspace lives in. When we're created, we're going to go ahead and create a host thread to run our program. We've got to get and set for the workspace root. And then the main thing that the debug adapter does is it dispatches requests. So the protocol server will get the network messages, turn them into these request objects, and then call this method for each one. And then our job is to build a response. So our default response is just a response. We're going to set the sequence number to match the request. We're going to copy the command into the response and set success to true. So if nothing else happens, we'll return this response, and it just is saying whatever that command was, it succeeded. So any commands that we don't actually understand, we're going to say that worked. We're going to call command parse to turn this into a command object. And then we will get the arguments. We're going to take the JSON of the arguments and turn it into an arguments object. And then we know there's only one thread running, right? So for now, our debugger does not support multiple threads. Our VM itself, I think, would work okay with multiple threads, but there's no way in our language to kick off a second thread, right? If the host thread has terminated, so if the program we're debugging has ended, we're going to just return that response as success for any commands that we receive. The program's already died. We're expecting a disconnect command to come in shortly because we have told VS Code that the program has died. So there may be some commands that come in between before VS Code's realize the program is finished. So if the host thread is terminated and the command we're looking at is not a disconnect, just return success. All right. Here are the commands that we support. So initialize is called when the debugger first starts up, and there's a bug in this Microsoft library that this is based on, which is one of the reasons I had to create my own version of that library. We're going to get the capabilities of the server and set the body to that. That's basically your job in the initialize, is tell the IDE what debug operations you support. So if we look at get capabilities, you can see some of the things we support. You can terminate the debug-e. You can do delayed stack trace loading. We support a restart request. So if you're in the middle of debugging and you click that restart button, it will restart the program. Evaluate for hovers. I say I support it, but we haven't actually implemented this yet. Read and write memory requests are allowed. That's what that memory view window will eventually do. There's a disassemble request. Once we get to brew, we'll be doing something like disassembly. Stepping granularity is also, I think, for that. And then instruction breakpoints is also for that disassembly stuff. So you can list the things you support here. Like we could support conditional breakpoints. Um, we could support data breakpoints. There are a bunch of things that VS Code supports. We're really doing pretty basic stuff in this debug adapter. Configuration done event, we don't need to do anything, so that's empty. Launch is the command that actually starts the program. All right, so this is where we're actually going to begin execution of the host thread. So we're going to get the arguments. One of them should be the current working directory. So this object is coming from the launch JSON configuration in VS Code, basically. And the current working directory is one of the things on that object. So that's how we know what our workspace root is. We're going to tell the host thread to compile its code. So this will turn around and call into our code. Basically, we're giving it the file we're going to compile, and it will compile it. If there's an error, we're going to print the stack trace here. We're also going to send back some events so that VS Code shows some errors in the IDE. Otherwise, we're going to verify our breakpoints, which will update them to valid lines if they're not already on valid lines. If our launch command asked us to stop on entry, we'll tell the host thread to do that, so it'll stop before the first command, first opcode is executed. And then here's where we actually kick off the host thread. So we're going to create a new Java thread that wraps that object and tell it to start. And we'll set launch to true. There's a threads command that asks us to tell VS Code what threads are running. And since we always just have one, there's that hard-coded threads object that we created up here, wherever that was. Here it is. We're going to return that. So there's one thread, and it's called main. There's a stack trace command. This is how we get the stack trace of our current location. So this is going to call the get stack frames function. We can get the current scopes. This will turn around and call get scopes on the host thread. Most of these things are going to pass through into the code we need to write. When we're listing variables, we're going to turn around and ask the host thread for the current variables. When breakpoints are being set, we're going to tell the host thread to set those breakpoints. And then if we're already running, we're going to call verify breakpoints, which may modify the line numbers that they're on. So the sequencing for breakpoints is a little weird because you can set breakpoints before we start running. And then when we start, we might realize they're on invalid lines. You can also already be running and set breakpoints. And you can still try to set them on an invalid line. And that's what we're handling right here. We can set instruction breakpoints. That's a disassembly thing. Disassemble, obviously, is that. Read and write memory we're not dealing with yet. Continue, next, step in, step out. These are all the buttons you can push in the debugger to go one line at a time or into a function or out of the function. And the host thread's going to handle all of those operations. If we're asked for source, that means that the debugger didn't realize that the editor it was looking at is the source code for the thing we're running. So if that command comes in, it means that like the paths didn't match, something weird happened with the current working directory. I have had problems where this happened, but if this happens, it really means there's a bug either in the extension or in this code. And then there's a disconnect when VS Code is stopping the debugger. So if they asked us to kill the debugee, then we're going to call terminate on the host thread. And if we get any other command, we're going to log it as an unsupported command and return an error unrecognized request. There's a little bit more support code here. The get stack frames is going to get the call stack from the host thread, and then it needs to massage this stuff into the format that the IDE wants to see. So we're going to start at the top of the stack, and we're only supposed to return a certain number of stack frames. So the IDE to save, it can be very expensive to calculate stack frames and get the variables in the stack frame and figure all that stuff out. So the IDE will only ask for the top few stack frames a lot of the time for efficiency. And that's what this is doing. We have to start at the top of the stack. We have to figure out how many frames we're supposed to be looking at, and then go get each frame, get the function from it, and then we're going to create a debug stack frame object, and we give it the frame number, counting from the top of the stack, I think. Is that right? And then get the function's display name so we know what the name of the stack frame is. We have to create a source object that describes the file that this stack frame is in, and the line number. So there's a file name, there's an absolute path, and then there's, I guess we don't care about the line number here. I don't know what that 0 is. And then here's the line number. So we're going to call the function to give us the source line for the program counter in this frame. And then we're also going to get the instruction pointer reference. That part's for disassembly. And then we add the frame to the list. So basically, we're building these debug stack frame objects that the adapter needs to see. So we ask our code for the call stack, and then we turn it into these objects. And we only return part of the stack if the IDE only asks for part of it. And then we have some events here. So when we call into the host thread, things will happen. And sometimes it's an event that needs to be sent back to the IDE. So if a breakpoint was updated, we need to tell VS Code about it. So it moves the red circle to the right line. So if breakpoints are updated, we're going to loop through and send these breakpoint events back to the IDE. If the program was stopped, we'll give it a reason that it was stopped, and we'll send back a stopped event. And we're also going to send this custom stopped event. That's where that, in the other video, I wasn't sure where this custom stop thing was coming from. That's what it is. And then if we exited, we'll also tell the IDE about that. We're going to send 2 events back. And then we have an output event. We can use this to print messages in the VS Code debug window. This is going to be handy later. And then I have a get stack trace, which is going to basically, if we have an exception and we want to send the information back to the IDE, we want to turn that into a string, and then we can send it back in one of these output events. So the other big piece of this is the host thread, right, which is going to be controlling the VM thread that's running. We have 4 states: running, stepping, suspended, or terminated. All right, so let's see. Suspended might only be used when we start up and we stop before the first line. I think stepping is the state when we're running and we're waiting to hit the next line, right? So sometimes, like if we say step over a function call, we need to run a bunch of instructions inside the function before it returns, and then we'll stop again. So we have these states that we need to worry about for our execution. I guess suspended is when we're actually stopped at a breakpoint or in between lines. And then terminated is pretty obvious. Okay, so this no stop frame, no, that's just a constant. We have our debug adapter. We have the execution engine that we're going to be implementing. We have our current file. We have the thread of execution. This is really like our VM thread. We have our current state. We have our step in granularity, which is told, the IDE tells us about that. And then we have a map that holds all the breakpoints. And we also have a list of breakpoints that are the unverified breakpoints. That's for disassembly. Instruction breakpoints are for disassembly. There's a max stop frame, and there is a next breakpoint ID. We're going to give breakpoints IDs as we go along. And then we have the stop on entry flag. The max stop frame is going to be used when we step out. When we step into a function call, we just go in, we run one instruction, right? We just run the call instruction and we stop. If we step over a normal opcode, we're just running one instruction. But if we do a step over and it's a function call, what we need to do is keep running as long as the stack has that extra frame on it, right? We've called into a function, we've added a stack frame. As long as we have that many stack frames or more, we're going to keep running instructions. And once the size of the stack goes back to where it was when we did the step over, it means we've returned and we're back, and we should stop again. So that's what this max stop frame is used for. Stop on entry is true by default, or actually no, if this function's called, we set it to true. Compile code is going to tell the execution engine to compile the file and remember the file name. We also have a set file that does that. We have this verify breakpoints. So here is the code that needs to take the breakpoints we were given, go through them, tell our code that we're going to implement about them, and find out if they're on valid lines. So here we're going to loop through the breakpoints by file. And for each file, we're going to go get the breakpoints by line. And then we're going to loop through those. And we're going to call the execution engine resolve function to make sure they're in a function. If they're not in a function, then we'll set verified to false. We'll put them in the updated list. We'll remove them from our map. So these breakpoints are going away. They're just not on valid lines. Otherwise, we will call the update breakpoint function that we need to implement. And then if it returns true, we're going to add them to the updated list. If it was not verified, we'll remove it from the list of breakpoints because we don't want to stop on that. And if the line has changed, we will add them to the moved list. And so then here at the end, for each moved breakpoint, we're going to update the breakpoints by line. And you can see I wasn't sure when I wrote this if the old entry still exists, and I'm not sure now either. Guess I'd have to go dig through the code. And then this is disassembly stuff. And then if there are updated breakpoints, we're going to send that event back to the IDE. And then here's our run method. This is what's going to actually run the VM thread and execute opcodes. Our entry point is either going to be main or main.main, depending on what language we're in. .s is going to be the assembly language thing we'll do later. Here we're going to tell the execution engine to start the thread, so that'll create a VM thread basically and get it ready to run. If we're at stop on entry, we're going to call the stop function and tell it the reason is because we are at entry. Otherwise, we're going to call stop if necessary. So that would do it if there's a breakpoint on the first line of the program, basically. And then while we're running, we're going to say if we're in the running or stepping mode, then we're going to call thread.step. And if it returns false, it means our program is done. So we're going to exit. If we get a VM exception, we're going to send that back to the IDE. That'll make it a lot easier for us to debug stuff later on when we're doing more complicated things and getting it wrong. If we catch any other exception, we're going to, so a VM exception will just get the message and send it back as an output message. If we get an exception that is not a VM exception, then we're going to get the whole stack trace and send it back to the IDE. So VM exceptions are ones we're throwing on purpose, and the message should tell us what's wrong. But other exceptions are like unexpected things, null pointer exceptions, whatever we screw up in the VM, and we need the whole stack trace for those because we want to be able to figure out where they came from. We'll call stop if necessary. If we're suspended, we're going to sleep for a second and let the loop go around again. So basically, if we're at a breakpoint, this loop's just going to keep going around sleeping, and then we'll eventually get a command from the IDE to step or continue execution. And if we get terminated, we're going to exit the thread. So stop if necessary, we're going to get the call stack. We're going to peek at the frame on the top. We're going to get the function for that frame. We're going to go get the file for that frame. We're going to be able to have internal files that don't really allow breakpoints later on. But for now, that doesn't make sense. And then we're going to look at breakpoints by file. And if the file doesn't exist, this will give us an empty hash map so it doesn't explode. And then we're going to look up by the source line. So we're going to take the program counter, convert it to a line number in the file. Then we're going to look that up and see if there's a breakpoint there, basically. And so if it's not null and we're at the first instruction on the line, which doesn't make sense yet, then we're going to stop, right? So basically, if we look up the file and then we look up the line we're on and there's an object there that's not null, that is a breakpoint and we need to stop. So we'll stop. Else, if we're not worried about instruction breakpoints yet, and if we're in stepping state, and if there is no stop frame, so this basically is used when we're stepping in. So if we're stepping in or we're just stepping over a normal line of code, in that case, we would stop. Or if the call stack is small enough that we are supposed to stop. So this is what I was talking about with step out. Basically, if you step out, the size of the stack should decrease. And so we're going to keep running until the stack has gotten small enough. Or if we do a step over on a function call, we're going to stop when the call stack gets back to the size it was. So in either of those cases, this is deciding when to stop. And then if we're doing instruction stepping or we're at the first instruction on the line. So you can ignore this if for now. Basically, if this is true, we're going to stop right now. So if we don't have a stop frame or this call stack is correct for when we need it to stop, then we will stop. And then here's our stop. We're going to set our state to suspended, set our max stop frame. We'll clear that. and then we'll tell the IDE that we stopped and what the reason was. If next is called, we're going to set our state to stepping, set our granularity to whatever was passed in, and we'll set our max stop frame to be whatever the current call stack is. Okay, so next is step over. So we're not going to stop until the stack frame is the same size as it is now. And then we'll call notify, which basically is going to, I think it just gets it's going to wake up this thread if it's sleeping, I believe. So if we're sleeping in that suspended state, we don't really want the wait. Yeah, this is what it is. So in our suspended, this wait 1000 is not really a sleep, right? It's a wait on the lock on the current object. And it will wait for up to a second, and then it will throw an exception if notify was never called. So no, that's not right. I think it probably just returns after a second. Anyway, it's going to wait for up to a second and then return. And if we call notify, the wait will end early, and I believe interrupted exception is thrown, so this will catch it, and then we'll continue. So basically, if you hit step, you don't want to have to wait a whole second between each call to step when you're trying to step through code. And so we're waking this wait up early. That's what notify is doing here. Where were we? Yeah, so we're on next. Step in. We're going to set the state to stepping, and we're going to notify right away, to let the execution actually happen. Step out, update the state. We're going to set our max stop frame to whatever the call stack is now -1. So when we return from the current stack frame, we will stop. And then if somebody hits continue, just let the program run to the next breakpoint. We'll set our state back to running. And again, notify to get out of that waiting state. Set breakpoints is going to populate our maps. So we're given a set breakpoints command from the IDE. We're going to look up the breakpoints for that file and create a new hash map if it's not already there, and clear it. Whenever we get this command, it sets all the breakpoints for a given file. So we clear all of those breakpoints, and then we're going to loop through, create breakpoint objects for each of them, assign an ID, and then put them in our breakpoints by line. And then later on, we can check and see if they're valid. Instruction breakpoints we'll see later. Get call stack turns around and calls get debug call stack on our current thread. Get scopes, that gets passed into code we need to write. Get variables, same thing. We're not worried about disassembly or read and write memory. If terminate is called, we'll set our state to terminated, wake up the wait. Join is going to, so this function is actually going to be called by a different thread. This is going to be called by the debug adapter. One thing I didn't really point out is any of the methods that are going to be called from a different thread need to be synchronized. So you'll notice a bunch of these are synchronized. These are methods that are called from the debug adapter. In our terminate, we're going to wake up the wait, and then we're going to call join, which will join the current thread to the host thread and wait for the host thread to die. So because we set the state to terminated, it should exit. And the current thread is the one the debug adapter is tied to. So we're going to wait for that thread to exit. And then if it does not successfully exit, I'm not sure what causes an interrupted exception here. I guess if notify is called while we're waiting for the thread to go away, that probably does it. Anyway, that's something we don't want to happen. Basically, set the state to terminated, tell the other thread to wake up so it sees this and exits. Then we call join to wait for it to exit, and then our debugger is terminated. Is there any other interesting code in here? We have this VM exception that we're going to use as a base class later on. We have this multi-execution engine. So once we add multiple languages, we'll use this. But this basically just wraps multiple execution engines and decides which one to use based on the file name of the thing we're debugging. We have this console class or console interface that lets us print strings. We're not using that yet. So I think that's about it. So as you can see, the debug adapter is a lot more complicated than writing the debug extension, right? So the client piece of the debugger is really all implemented for us in VS Code. And the server part is very language specific and needs to be written by whoever is writing the runtime for the language.